Okay, so one more, what's the relationship? So these are two Newman projections again, much like the last problem. So once again, you need to figure out if they're superimposable from the start. If there's any obvious difference, look for an obvious difference. There's no obvious difference. There's one bromine, one chlorine in both molecules. There's a carbon. There's 1, 2, 3, 4 carbons, right? The two methyls, the front and back carbons in the Newman projection. So 4 carbons, Br and a Cl in both. 0 unsaturations. On the right, there's 2 methyls, front and back carbon, so C4, Br, Cl, 0 unsaturations. So the two molecules are isomers. Are they superimposable? If we just slide this one over, front carbon, the front carbon matches, but the back carbon, the methyls are off. If you flip this over, the back carbon matches, but then the front carbon doesn't. So they're not immediate. It's not immediately clear that they're superimposable. It doesn't look like they're superimposable. So I'm going to continue under the assumption that they're not. How about connectivity? Well, we have a methyl, 2 methyls on the back carbon, a bromine and a chlorine on the front carbon. So that would be CH, BrCl, and then CH with 2 methyls. 2 methyls on the back carbon on the right, a chlorine and a bromine on the front carbon. So they're connected the same. So they're isomers of some sort. They're not constitutional isomers. They're isomeric. They're not the same. They're not constitutional isomers. Again, that leaves us conformational isomers. They could be different conformations of the same compound. They could be mirror images of each other and be enantiomers. They could be diastereomers. So how many chiral centers are there? Hit pause if you want. Figure out how many chiral centers there are. Okay, front carbon, the back. Let's do the back carbon first. 2 methyls on the back carbon, it's not chiral. Two identical groups on one carbon, it's not. That carbon is not chiral. Front carbon has an H, a chlorine, and a bromine. What's the fourth thing it's bonded to? It's bonded to the back carbon. Back carbon, so that's a carbon. Br, Cl, H, and C. 4 different things. The front carbon is chiral. Same thing here. Br, H, Cl, back carbon. That front carbon is chiral. So now, if you have a chiral atom, and you can't immediately tell if they're mirror images or not, what you need to do is assign R or S, or do some other sort of identical comparison. In this case, rather than assign R and S, the easiest thing to do is just look at, we've got the back carbon away, we've got the back carbon away on the right. Let's just go by priority of what we can see. So bromine, chlorine, H. So if we go bromine to chlorine to H, that's a clockwise circle. On the right, bromine to chlorine to H is a clockwise circle. The configuration of the front carbon, the front chiral carbon in these two structures is the same. If you want, hit pause and you can go through and calculate R and S and come up with that. I didn't just calculate R and S. I'm just holding it in one conformation with the same priority group back. Okay. So again, there's one chiral center, there's no isomerizable double bonds. 2 to the 1 is 2, so there's 2 possible stereoisomers. So it could be an enantiomer. Can't be a diastereomer. There's not enough possible stereoisomers. Okay, so the molecule's chiral, there's no plane of symmetry. So these are either different conformations of the same molecule or they're enantiomers. Well, I actually answered that question. The conformation, the absolute configuration of the front carbon is the same. So they're not enantiomers. That leaves conformations. So you want to clarify that. I haven't written anything down. I hope this video is not just me rambling. What you can do is hold the front carbon the same. The front carbon actually matches in the other two. If we rotate the back carbon 120 degrees, this H comes to here, the methyl comes to here, this methyl comes to here, and we get this structure. These are conformational isomers. That is, they're 2 different conformations of the same molecule. If we had this molecule in a bottle, we would have both of these in fairly abundant concentration. Which one is most stable? Which conformation is most stable? Hit pause and think about that. Okay, if you're back, the conformation on the right is actually the most stable. So you might be wondering, there's 2, what's the big group on the front carbon? Big group on the front carbon is bromine. What's the big group what's the big group on the back carbon? Methyl, but there's 2 of them. And so, well, actually this does work out. Bromine is anti to one of the big groups on the right. The other way to think about this is count the Gauss interactions. And so there's, on the left, there are 3 Gauss interactions between non-hydrogen substituents. On the right, there's only 2. So those Gauss interactions have a small energetic penalty, so you want to minimize them so the structure on the right is most stable.